Hey everybody, this is a lecture on a new module over what I would call optics. Basically, it's chapter 33 and 34. Chapter 33 is about, starts out as electromagnetic waves. Um, but if the wavelength is short enough, you can treat the waves as not spreading or doing other wave-like things like interference, and we can think of them as traveling in rays. And we'll talk about that. Chapter 34 is about using those rays to look at optical systems like lenses or mirrors. And so we'll talk about that in later lectures. For today, I want to talk about the phenomena of refraction and reflection. So let me share the screen. And so we can see here that we're going to talk about reflection and refraction. And before I go into that, let me talk about again, the idea of a ray or a wave propagation. Uh, as we've talked about before, you can have waves that travel out spherically. And what I would say is that these are the wave fronts. These kind of pinkish lines here are the wave fronts. And then the normal or perpendicular to the waves kind of indicate the direction that the wave is traveling at that point on the wave. Um, the right figure here are what we call plane waves. And so the wave fronts are all perpendicular. And then the wave normal, or the wave propagation vector, you might call it, is again perpendicular to those. This would be kind of similar to the waves coming across the parallel beach, right? And so what we're going to look at is light traveling in this direction, but the waves are perpendicular to the direction that it's traveling. And if the wavelength is short enough, you can neglect things that we will discuss later, like diffraction. Typically, a wave will spread when it goes through an opening, but it doesn't spread much if the wavelength is really small. We're going to talk about rays. So we might think about a light traveling in one direction, and then if it changes direction, it goes in the direction of these wave normals. Uh, so when we talk about reflection, basically we have kind of two kinds. We have a normal reflection, and if you can look here, I've got a wave traveling in a first medium one, and then it hits an interface between it and another medium two. If it goes normal, it's hitting the interface perpendicular and bounces straight back. So you can see the right angle here. Normal incidence is perpendicular, orthogonal, or right, or 90 degrees. And we're always going to measure any angles relative to this normal direction, normal to the interface. So when we go to what's called oblique incidence, we have a ray, right, a wave front coming in. And notice this, I've only drawn one wave front, so the plane wave fronts are perpendicular to that. But it's coming in at an angle. And this angle is what we would call the angle of incidence. Now, it's going to hit and reflect off of that interface. It also might transmit somewhat through, and we will have what's called refraction as it transmits through to the second interface. But first of all, let's look at the angle of incidence and angle of reflection again. So the angle of incidence, I've got my incident ray coming into my air-water interface here. Angle of incidence is this one. Angle of reflection is the angle at which the ray bounces off. Right, so the incident ray is going to come in, and the reflected ray is going to bounce off at the same angle. So the law of reflection is that the angle of incidence equals the angle of reflection. And again, the wavefronts are perpendicular or normal to the rays. Now, another phenomena that happens is called refraction. And as you can see, this ray that gets transmitted into the water has a different angle than the angle of incidence. We say that that ray is refracted. It's bent from the direction that it would go if the interface was not there. And we're going to talk more about that. But before I get to refraction, a couple of other types of reflection. We can have what's called specular reflection, where rays just bounce off. Remember, law of reflection is incident angle equals reflected. So they're bouncing at the same angle, but they're bouncing off of a smooth surface. So if I get light coming in and bouncing off something like this, the rays don't get dispersed, and I can see a very clear image of it, of the object. Maybe it's a leaf. Diffuse reflection happens if there's a rough surface, like in the second picture. So some of the rays have different incident angles normal to the interface at which they are hitting, right? The red one here, the normal is very much at an angle, or it's pretty flat for the green one. So they're going to bounce off in all different directions, and kind of the information is going to get jumbled up, and maybe the image is not quite as clear. We typically see reflected light. Okay, and so now let's go to refraction. So refraction is that bending of the light ray as it goes from one medium to another. And we're going to talk a little bit about why it occurs. But one thing I want to point out is as it comes in, if it's going from a faster medium to a slower, it bends inward toward the normal. If it's coming out, say, of a slower medium out to a faster medium, it is going to bend away from the normal. Now, when we're talking about light, what do I mean by fast and slow? Now, the speed of light itself in vacuum is what I call c, and it's about 3 times 10 to the 8 meters per second, right? This is speed of light in vacuum. But what happens when light goes into a different medium is that it slows down. And so, for example, air has a speed very close to the speed of light. It's not much slower than 3 times 10 to the 8, but glass is somewhat slower. So I'm going to go from a fast to a slow medium. Another example here of what happens, for example, let's say you're trying to catch a fish and you're looking into the water. Well, the fish, the light coming from the fish that you're going to see is coming up, but it's going to bend away from the normal because it's going from a slower medium to a faster air medium, right? And what your brain always interpolates, it always thinks the ray of light has come from straight. It can't calculate the refraction. So it sees the fish here, which is a little shallower than the real position of the fish. So if you were hunting in this situation, you would need to aim lower than what you're seeing due to that refracted light. Okay, so again, why does it occur? Well, this is an analogy is, let's say you have a car and it's going from a road, which is concrete. It can travel faster on that road. If it goes into mud, you can see it's coming at an angle of incidence. This wheel is going to catch the mud first and be pulled to the right. And so it's going to bend toward the normal. Another picture here. Now, if it went the other way, if you went from the mud out into the road, your tire would hit the road and start to speed up before the rest of the car does, and it would move the opposite direction. The same thing happens for light, except we're not talking about the wheels of the car. We're talking about the wave fronts, right? The wave front that is kind of hitting the slower medium first is going to slow down before that part of the wave front that's still in the faster medium. And so this is kind of an analogy, but what is the mathematical law that governs this? It's called Snell's law. Now, Snell's law can be written in a few different ways. It is dependent on the speed in the medium. So one way to write it is that the speed of the incident medium divided by the speed of the transmitted medium, the ratio, is equal to the sine of the incident angle over the sine of the transmitted angle. Now, typically when we're talking about light, this also happens for sound. So this is a typical way to write this for sound waves. But actually, when we're talking about light waves, what we like to define is something called the index of refraction, and I'm going to call that n. And n is the ratio of the speed of light to the actual speed in the medium. Right? So, for example, n of water is about 1.33. So this means that the speed of light is in vacuum is 1.33 times faster than the speed in the medium, right? And so if I kind of plug this in, I can see that what I will get is nt over Ni is equal to sine theta I over sine theta t. All right, so it's reversed. My speed incident speed incident over or speed transmitted becomes index transmitted over index incident because of the inverse relation between index and the speed. So another way that is often written is Ni sine theta I equals Nt sine theta t. So this is Snell's law. This will tell me, if I know the incident angle and the indices of refraction of the media, how to calculate the refracted angle, for example. And so you can see, just another way of writing it here. So what we're going to do is use that. And I will do a problem and example here in a moment. But one curious thing I want to point out is something called total internal reflection. And this happens when the light stays actually within the incident medium and cannot get out. So what do I mean by this? Okay, so for example, in this image here, I have an incident ray coming into water, or from water out to the air maybe. So it's going from a slow to a fast medium. Therefore, it bends away from the normal direction. All right, so let's use the Ni sine theta I equals Nt sine theta t version of Snell's law. As this angle gets bigger, this refracted ray bends more and more until it actually reaches 90 degrees. So my transmitted angle becomes sine of 90 at what I call theta c, or the critical angle. Right, and so sine of 90 is 1. So my critical angle, the sine of the critical angle, is just going to be 1, or Nt, over Ni. Now, what this means is once we get to the critical angle, since the refracted angle or the transmitted angle is 90, no light comes out of the water. It is totally internally reflected. And any angle above the critical angle, as I make this theta incident here bigger, is going to give total internal reflection. I will never get light out of the medium if my incident angle is above the critical angle. Now notice this only happens if I'm going from an index N1, which is bigger than N2, from a faster medium to a slower. It doesn't happen the other way because you'll never get a 90-degree transmitted angle because it's bending the opposite way, right? You go to 0, not to 90. If you're going from fast to slow. But it can happen, for example, in glass or in a diamond. If I have light inside of a diamond, diamond has a pretty large critical angle. So many of the rays that are trying to get out of the diamond are internally reflected, and I get a lot of bouncing around in there, and that actually contributes to the sparkly nature of the diamond. So hopefully that makes sense as far as total internal reflection, but let's do an example which kind of combines both the refraction and total internal reflection parts. So again, this is an example from the book. This figure depicts a simplistic optical fiber, right? In fiber optics, it's basically just a glass type tube. It has a plastic tube. It has a plastic core with an index of 1.58, and it's surrounded by a plastic sheath with a slightly lower index. So it's going to go a little slower in the outer sheath than it does in the core of the fiber optic. So a light ray comes in and it's incident right here, and then it refracts. And the question is, at point A, where it counters the core sheath boundary, the ray is going to go undergo total internal reflection. There's no loss of light out into the sheath. What is the maximum value of this incident angle that allows total internal reflection at A? So the first thing we need to find is, what is the critical angle, right? And if I'm looking at the critical angle, I'm looking at point A. And so again, I'm going to use Snell's law, Ni sine theta I equals Nt sine theta t. And I have, in fact, that theta t is equal to 90. So the sine of my critical angle is n t over ni. So it's equal to 1. Oops, let's see, I think, yeah, so we have 1.53 over 1.58. If I take the inverse sine of this and make sure I'm in degrees, I get an angle of 75.6 degrees. So this is my critical angle. It's a very big critical angle. Anything above that angle, as far as this goes, right, at this interface, anything bigger than 75.6 degrees is going to be totally internally reflected. Now, the thing is that if I increase my theta here, eventually it's gonna bend in and it'll exceed that critical angle, and I won't get total internal reflection. But the way that I can get the maximum theta is just to, again, use Snell's law for this interface. So my theta there is my incident angle, and my N1 is air. So it's 1 sine of theta is equal to N1 sine of theta transmitted, right? And now theta transmitted is going to be this. But the thing to realize is that my transmitted angle is definitely related to this critical angle. In fact, it is 90 minus 75.6. You can see that, right? So this angle forms a right triangle with the critical angle. So this angle, theta t, is 90 minus 75.6, which gives me 15.4 degrees. So if I'm at that point where I'm just at the critical angle, my theta t is 15.4 degrees, and I can solve for theta. So theta turns out to be 23.2 degrees. And there's my answer. Any smaller angle than that, or sorry, any bigger angle than that is going to give me not the total internal reflection. So this is just an example of using Snell's law in both the case of total internal reflection at the core sheath boundary, as well as just Snell's law in general. So you'll see problems of both of these in the homework.